Okay, good evening, guys. Welcome to this core science chemistry revision session. The session will last approximately an hour. If you've got a pen and paper handy, that will help you because I'll ask you some questions throughout to check your understanding. In this revision session, I'm going to cover the first half of the C1 topic. I will do another revision session and post a video which covers the second half. So let's get started. The first thing that I want to talk about is the periodic table. Now, you will get this periodic table on your data sheet in your exam, but the one thing people forget to do is use this key here. This key is vital. It gives you so much information. What you need to remember is that this key tells you what each of the things in the boxes mean. So, for example, relative atomic mass is the top number. Atomic symbol is the second bit down. The name of the element is just below. And then the proton number is just below that. So simply forgetting to use this key makes things really difficult for people. So you need to remember that when you're doing your exam. And don't just put this paper to one side, make good use of it. So let's talk about what these things mean. Well, the first thing that I want to talk about is this one here, the atomic or the proton number. Now the clue's in the name. This number on the bottom of each element tells you how many protons. It tells you the number of protons that element has. The bit that you need to remember is that is also equal to the number of electrons. So in every single atom that's shown on this periodic table, every single element, the number of protons equals the number of electrons. So if you forget this, or you're likely to forget it, you might want to, as soon as you open your paper, you might want to write on your data sheet that this is the number of protons and the number of electrons. Now the atomic mass is made up of the protons added to the neutrons, okay? Because we'll talk about why a little bit later in the next slide when we talk about atoms and what atoms look like, but for now I'll just write that down. We'll refer back to it in a minute. So a few things that we need to know about the periodic table. We need to know about this first group here as well. This first group is called the alkali metals. And these are quite reactive metals. They are in group 1. We call the columns on the periodic table groups. And we call the rows on the periodic table periods. Okay, so that's one to remember. Another group that we need to know about is this group over here, which is the noble gases. So all of these gases down here are unreactive, and they are in group 0. And they are called the noble gases. A big chunk that we need to remember is in the middle of the periodic table, and it's this chunk here, which are the transition metals. So all of these metals in the middle here are transition metals, and we'll come across these later on in this tutorial. So these are really important to remember. They are called transition metals. Now, on your periodic table, you won't get a line that separates the metals and non-metals. They're not that nice in the exam, but you have to remember that it's roughly around here. This imaginary line here that separates the metals and the non-metals. And sometimes there's quite an easy question that will say, where on the periodic table are the metals? And what you need to remember is that everything to the left-hand side of this line are all metals. So everything to the left here are all metals, and everything to the right of that line, so boron and all of these down here, bromine and krypton, are all non-metals. Now, importantly, we don't call these gases, even though lots of them are gases at room temperatures, we call them non-metals because there are things that are solid at room temperature, like carbon and sulfur and things like that. So they're metals and non-metals, and this big block of metals in the middle are the transition metals. Now, really importantly, don't guess if they say to you, where are the metals? Have a look at the names. Have a look for the common ones that you know about. There's copper there, there's magnesium there. there's titanium there, you know that all the metals are on this side, whereas over here you've got things like oxygen and chlorine, and you know that they are non-metals. Another really important thing is that each of these elements, which is a type of atom, so an element is a type of atom, hence why this is called the periodic table of elements. Each element starts with a capital letter. For example, aluminium is capital A, then lowercase l, and if the letter's on its own, then it is just a capital. Now, where this becomes really important is if we look at something like cobalt here, because cobalt is capital C, lowercase o for cobalt. And if you wrote them as two capitals, you'd be talking about something completely different. You'd be talking about carbon monoxide, okay? Carbon bonded with oxygen. So it's really important that you get that the right way round. So we'll refer back to this and the importance of this periodic table a little bit later on, but I can't stress enough how important it is to use this key. And you know then that top number is the mass and the bottom number is the number of protons. Okay, moving on then, we're going to talk about atoms, and that will link back to what we just said about the periodic table. So there are over 100 different types of atoms, and those are in the periodic table, and the types of atoms are called elements. But the basic structure is similar. They will have a nucleus in the middle, and this nucleus will contain protons and neutrons. And the protons, I'm just going to put as a little plus here in the middle. And the neutrons I'm just going to put as just plain circles like that. I'll explain why in a minute. So you need to know that the centre is called the nucleus, and that's where the protons and neutrons are. Around the outside then, you get electron shells. So I can draw some in here. So you get these electron shells around the outside, and you, depending on the number of electrons you've got, you might have one shell or you might have several shells, a little bit like this, going over top of each other. Okay, but we're going to concentrate on the basic atom here. So we have the nucleus in the middle containing the protons and the neutrons, and around the outside is where you find the electrons. And in an atom, the number of electrons, like we said before, so number of electrons is the same as the number of protons. And what that means is the number of negative charges, we'll discuss this in a minute, is the same as the number of positive charges. So there is no overall charge on an atom because the number of electrons and the number of protons is the same. So this is the basic structure we got. I want you to try and remember the atom as, if you think about a football pitch, in the middle of the football pitch, you've got the centre spot where you'd put the football. That is what I'd like you to think of the middle of the atom, the nucleus, as being a football on the middle of that centre spot. That is where all the mass is. Okay, so in the nucleus here, we've got all the mass. So think of that as like a big heavy football in the middle. Then around the outside are the electrons, and they're right out. If you think about Wembley Stadium, they'll be right out in the highest tiers, okay, around the outside. Most of the atom is empty space, and these electrons will be whizzing around like almost like little fairies around the outside. That will help you to remember a couple of things about these particles in an atom. So we'll summarize them over here. You need to know the charges on the protons, electrons, and neutrons and their relative mass. That just means compared to each other, what number can we give them for mass? So let's talk charges first of all. Protons have a charge of +1. If you just put plus, you will not get the mark in the exam. So you must say +1. Electrons have a charge of -1. And neutrons have no charge. They are neutral. So neutron is neutral. Protons, P is positive, and the only other one you need to remember is electron being negative. So P for positive, neut for neutral, and remember that the electron is negative. For the mass, now we can't give them a proper number for their mass because their mass is so tiny. But instead, what we do is we say their mass, what is their mass relative to each other? So I just had a question to say which one's, while we're there, which one is best way to remember which one's positive and which one's negative. I tend to remember is the P is for positive, the neut is for neutral, like I said, and then that leaves the one left over as negative. Okay. On the right hand side, then we're talking about mass. Now, relative to each other, like I said before, the stuff in the middle of the atom is the stuff with mass, and protons and neutrons have the same mass. So that we just say their mass is 1, which means it's the same relative to each other. The electron, on the other hand, like I said, whizzing around these higher tiers of Wembley Stadium, they have hardly any mass at all. In fact, their mass is so tiny, we get away with simply writing very small. Or you would get the mark if you said 0 as well, but strictly very small is better. Now we're going to get on to drawing atoms and showing their electron structure. Now, when you do this, you don't have to draw the nucleus like I did over here. You only have to draw the electron structure. And to do that, you will need your periodic table to tell you how many electrons an atom has. So as before, we've got our key, and I've given you 2 elements here. We need to think about the proton number. We need to think about this rule over here. The number of electrons in an atom equals the number of protons. So if we have a look at our proton number, that will also tell us the number of electrons. So we know in boron there's 5 electrons, and in argon there are 18 electrons. So when we start drawing these, we need to know a couple of rules about where the electrons can go. Now, the first one is that the inner shell can hold up to 2 electrons, only 2, and the outer shell can hold up to 8 electrons. So we're going to need to draw another ring on this argon atom at the bottom. So we've got 3 rings on this one. I'll just draw that again, hang on. To draw another ring, so we've got 3 rings. And then we can start drawing in our electrons. Now, normally we draw electrons as crosses. That's the simplest way. We draw electrons just like crosses. And sometimes you'll see them as dots as well. So let's look at boron first of all. We need to draw 5 electrons, and let's stick to this rule. So the inner shell can have a maximum of 2 electrons. That's 2 used up. And then the outer shell can have a up to 8. But we've only got to draw 5. So we draw our electrons on 1, 2, 3. And that would be the electron structure of boron. Now, don't forget that you don't need to draw the nucleus. You're just drawing the electron structure. For argon, then, we start with that same rule. We've got to draw 18 electrons. So we start with 2 in the middle. And that's full up now. We can't draw any more because of that rule. On the outside, we can draw up to 8. So we start drawing them in. I tend to draw them in pairs like this. It just tends to make it a little bit neater. And then on the outside, now we've used 10, we've got 8 electrons still to give. And there we have the electron structure of argon. And this brings about my final point in relation to atoms in the periodic table. And that is to do with the number of electrons in the outer shell. Okay, the number of electrons in the outer shell, I'll write it over here, the number of electrons in outer shell is the same as the group number. So we can look at this atom and we can see that boron must be in group 1, 2, 3 because it has 3 electrons in its outer shell. Where it becomes a little confusing is with these noble gases like argon. Argon has 8 electrons in its outer shell, but you don't call it group 8 anymore. You used to, but you don't. We now call it group 0. And this is because in group 0 you also have helium, which is like this atom over here. It only has 2 electrons, but helium has only 1 shell. Therefore, its outer shell is full. So everything in the noble gases in group 0 has a full outer shell. But you can't call it group 8 strictly because you've got something in there with only 2 electrons. So lots to remember. These questions on atoms and periodic table tend to come up as the first couple of questions to kind of ease you in. So really importantly, make sure you're using your periodic table to help for these questions. Okay, here's where the pen and paper comes in handy. I've got a couple of questions here for you to answer. Have a go at these. I'll check the questions whilst you're doing that, and then I'll come back and answer them with you. Okay, just had a question that says, what's the best way to remember that the electrons have a small mass and the others are 1? Really good question. I think if you remember that football pitch analogy where the nucleus of the atom is in the middle of the pitch where the football would be, and the electrons are like fairies whizzing around the outside, that'll help you remember that all the mass is in the middle, and then the electrons, like the fairies, have very little mass just whizzing around the outside. Also, if you remember that the relative atomic mass is the number of protons plus neutrons, which will be helpful for one of these questions, that will help you remember that the mass of each of those is 1, because you simply add them up. Okay, let's go through these questions then. Question 1 says, how many electrons does nitrogen have in its outer shell? Well, we look here, nitrogen is in group 5, therefore it has 5 electrons in its outer shell. The second question, draw the electron structure of sulfur. So we start by looking at sulfur. We have a look at how many protons it's got, and remember that that's always the number of electrons as well. So we know that we've got to draw 16 electrons. So we start off with a middle shell with 2, add a second shell with 8, and then we have a final shell with 6 on. And our final check is that sulfur is in group 6, so 6 electrons in its outer shell. I'll just add as well that the period tells you how many rings you need to draw. So this is period 1. It only contains hydrogen and helium. So that's why it's a bit confusing for some people sometimes. Some people start counting that that's period 1. It's not. This one is. So that's period 1, 2, and 3. So sulfur has 1, 2, 3 rings. How many protons does aluminium have? Well, we simply just look at the proton number, 13. And finally, how many neutrons does phosphorus have? Now, this relates to the fact that we're looking at the relative atomic mass, okay? And we said that this was the protons added to the neutrons, so the masses of all the protons added to the neutrons. So to work out the number of neutrons in phosphorus, we look at phosphorus, we see, well, the number of protons and neutrons is 31, and the number of protons is 15. So if I take away the protons from the protons and neutrons, I will get 16. So here we had the protons and neutrons. Here we had the protons. If I take that away from that one, that will give me the answer of 16 neutrons. Okay, so very well done if you got those questions correct. We're going to move on now to talk about compounds. So really important definition here, I've seen it in the exam so many times for 2 marks, is the definition of a compound. And for a compound, you need that idea that there's 2 or more elements chemically bonded together. Really, really common definition. 2 or more elements chemically bonded together. So basically, there's 2 or more different things from the periodic table bonding together. Now, we don't need to go in much detail about bonding for C1, but we need to have an appreciation of these 2 things, ionic bonding and covalent bonding. In ionic bonding, that is between metals and non-metals, whereas covalent bonding is between non-metals only. So if I give you a couple of examples, you might see something like CaCl2 or NaCl for an ionic compound. So we've got 2 different metals, 2 different elements chemically bonded together. One is a metal, sodium in this case, and one is a non-metal. And these are both examples of ionic compounds. Something only containing non-metals then might be something like CH4, methane, or ammonia, NH3, or something like H2O, when you've got 2 non-metals bonding together. So ion, the clue is in the name. Ionic bonding is all to do with ions, okay? And these are formed when atoms gain or lose electrons. And for your exam, you need to remember that the metal ions lose electrons, metal atoms, lose electrons and become positive. And on the other hand, non-metals gain electrons and become negative because they're gaining a negative charge. So overall, they're more negative. And it's these charged particles then that attract each other. For example, we've got Na plus and Cl minus, and they are then attracted to each other in this ionic bond. Okay. On the other hand, covalent is all to do with sharing electrons. Okay, so I think of it like covalent, like cozy, or cohabiting, like sharing together. Cozy electrons, they're sharing. Okay, so covalent bonding is between non-metals. And for example, if you take something like HCl, hydrogen chloride, 2 non-metals bonding, that's when they want to get a full outer shell. So if we have hydrogen, for example, here, bonding to chlorine, hydrogen has 1 electron, shown by the cross. Chlorine has 7 electrons. And they will be covalently bonded because they're sharing this pair of electrons just here. Now, for C1, you won't be asked to draw these covalent diagrams, but you will need to recognise this is covalent, or you might need to recognise something like this, a molecule here, as being covalent, okay, because it's 2 non-metals bonding together. Now, the final thing, this is something that people get wrong quite a lot of the time, is the idea that compounds that are covalently bonded are called molecules. So often this gets, people overlook this idea and then they get it wrong, okay? So molecules here, they that are covalently bonded, compounds that are covalently bonded are called molecules, okay? So anything that's sharing electron, those non-metals bonding together are molecules. So I've just been asked to repeat what this says just under here because of my scruffy writing. So it says metal atoms lose electrons and become positive ions, and non-metals gain electrons and become negative ions, and that's how they bond in ionic bonding. Okay, so I hope you've written down this definition because this is really common coming up, and I hope you now understand that molecules are covalently bonded compounds. Okay, here are a few questions for you to try while I check the messages. Have a go at these and I'll come back and go through them with you in just a sec. Okay, I've just had one question that says, I thought electrons were the top number, take away the bottom number. No, that's neutrons, okay? Electrons is the same number as the proton number. Because what you need to remember is that atoms have no overall charge, so the number of protons has to be the same as the number of electrons. So if you think you're going to forget that, what I'd do is write on your data sheet straight away as you get into the exam, where it says proton number, I'd write underneath also electrons, okay? And next to the mass, I might write protons plus neutrons to remind me. Okay, another question that says, why can't metals gain electrons and non-metals lose electrons in ionic bonds? Now, that's a really good question. I try and think of it as what is it easiest for the atom to do? And if you look at the periodic table, we're talking about metals having 1, 2, or perhaps in rare cases 3 electrons in their outer shell. So it's easier for them to lose electrons, to have a complete outer shell underneath, than it is to gain electrons. Think about sodium, for example. Sodium's in group 1, has 1 electron, so it's easier for sodium to lose that electron, and therefore its next shell down will be full, than it is for it to gain 7 electrons. Okay, so it always happens that way around. Okay, let's go through these questions then. What is a compound made out of non-metals called? That is a molecule. What type of bond do the lines represent in the diagram? I've seen this so many times. Yes, they are a single bond, but also because they are 2 non-metals bonding together, they also are a covalent bond. So you could put covalent or single covalent is fine. What type of bonding occurs between metals and non-metals? That is ionic bonding. And do atoms lose or gain electrons to form ions? They lose electrons, and like I said before, that's because that's the easiest thing for it to do, to then have a full outer shell underneath. Okay, so very well done if you've got those correct. We're now going to move on to the limestone cycle. Now, there's quite a few things that we need to remember about the limestone cycle. First of all, you need to recognise limestone in this form, calcium carbonate. So you need to know the chemical formula for calcium carbonate, okay, which is limestone. And we need to think about a few reactions that go on in this process and some of the uses of limestone. So we can see here we've got calcium, and then the carbonate bit is CO3. Now the first reaction that we're going to do is to make calcium oxide. You should be able to name these as well. So calcium from that element, and when it's bonded with oxygen, we don't call it calcium oxygen, we call it calcium oxide. So the first thing that we're going to look at is the reaction to make this calcium oxide from calcium carbonate. And you can kind of see from looking at the formulas about what's going to happen. Because if we break down calcium carbonate into calcium oxide, hopefully you can see that we've used up 1 calcium atom, 1 oxygen atom. So we're going to be left with carbon dioxide because we've got a C and 2 O's left. So the reaction that we've actually got taking place is calcium carbonate breaks down into calcium oxide plus carbon dioxide. And for the exam, you need to know that this type of reaction is called a thermal decomposition reaction. And we can break down these words to think about what it means. Thermal is the same as heat, and decomposition is breaking down. So all we're talking about here is using heat to break something down. That's exactly what you do. You heat up the calcium carbonate and you break it down into these 2 products. So sometimes they might say in exam, what type of reaction breaks down the reactant with heat? You need to remember these 2 words, thermal decomposition. And you'll produce carbon dioxide, and this will come up so much in your exam. If possible, link that to the idea of global warming, and that carbon dioxide levels and increasing levels are causing global warming. So we've now got a calcium oxide. We're going to want to then have a look how we're going to get to something called calcium hydroxide. What I'd recommend for you to do is look at the chemical formula here, and then you can have a look what's going on. So CaO to CaOH2, calcium hydroxide. How would we get there? Well, let's have a look at the extra letters we've got. We've got 2 oxygens, 2 hydrogens, and we only had 1 oxygen up here, so we must have added water. And this reaction, when you add water, is called a hydration reaction. Okay, so just like when you drink water, that's why I remember it. If you drink water, you're hydrating yourself. That'll help you remember that this reaction is a hydration reaction. And what we've got going on is calcium oxide being added to water, H2O, so it should be capital, to make this calcium hydroxide. Then what happens at this stage is this is a solid, and so all of these at the time. But if we add a little bit more water, we can then make aqueous calcium hydroxide. You can see it's exactly the same, but it just means if we add more water, we can then dissolve that in the water. And this you would have used in the lab before. This is actually called lime water. And this might be a little bit of a light bulb moment for you, but it will help you realise why lime water goes cloudy when you add carbon dioxide. Because if we add carbon dioxide to this, that will complete our cycle and get us back to calcium carbonate. And that's the reason why lime water goes cloudy when you add calcium carbonate, is because you end up with this solid calcium carbonate as a precipitate in there. So a couple of important uses of these products then. Calcium hydroxide is used to neutralise acidic soil. So farmers use it a lot to neutralise acidic soils. So that must be an alkali used then to neutralise those soils. Loads of important things coming up in here, especially remember these 2 reactions, thermal decomposition, when you break something down with heat. You can tell it's a thermal decomposition because look, it's not reacting with anything. It just got calcium carbonate and there's an arrow straight away. It's not reacting with anything. So you're just breaking it down with heat. And this hydration reaction when you're adding water. Okay, so there's a few uses of limestone. Hang on, let's go back. There are a few uses of limestone. First of all, we can make cement out of limestone if we heat limestone with clay. These are a bit laborious to remember. I would recommend you writing these on a post-it note on your wall to try and remember these. But I'll try and sort of work your way through them to give you a couple of clues on how to remember them. So limestone is heated with clay to make cement, so a useful product. Mortar is the stuff that you get between bricks. So where you see bricks together, the stuff in the middle is mortar. And mortar is made from mixing cement with sand, or in other words, the limestone and clay, and also sand. And the way I remember this, if you rub your finger across the bricks, you can feel that it's got a sandy texture. You can feel the sand in there. So that might help you remember that this is the one that you make by adding sand. And you still need the cement to stick the bricks together, but that sand is in there as well. And then finally, concrete. This is the really strong product that you make out concrete. And to do that, you've got one step up. You have the limestone and the clay and the sand as well, and the aggregate. Aggregate are small stones and gravelly bits to make that concrete really hard. So as well as limestone being useful for building buildings, lots of buildings are made out of limestone. They also have these 3 very useful products as well. Really tricky to remember these. I'd recommend writing them down and putting them on your wall, and just using that idea of running your finger between a brick to remember that's the one to do with sand. Moving on then to look at the advantages and disadvantages of quarrying. Now, to get limestone out, to be able to make magnificent buildings like this with the limestone, or to be able to make useful products like we've just discussed, we need to dig massive, great big holes in our environment. Hopefully now you'll be able to think of a few advantages and disadvantages for quarrying and making these massive holes in the environment. So whilst I look at a couple of messages, if you just try and jot down a couple of advantages and disadvantages, and then we'll just go through them. Okay, so advantages, we'd have things like local jobs. Now, I have seen examiners not allow jobs. Okay, so you must make sure that you're talking about the fact that the jobs are local, and that's an advantage for those people living around the quarry. So if you have written jobs, try and make sure you do get that local in there, just in case they're fussy again like that. Other things, they make useful building materials. So like the cement and mortar and concrete that we're talking about, but also in its natural form for building buildings. It can make products to neutralize acidic soils. So that calcium hydroxide that we're talking about before. And also this limestone is sometimes used in power stations as well to help neutralize any sulfur dioxide coming off of the power station, which is going to reduce acid rain as well. For our disadvantages, there's loads of things we can put. We put this an eyesore, that there's loads of noise pollution, that there's loads of dust pollution coming out of these big quarries, that it destroys habitats, and things like that there's going to be loads more heavy lorry and truck traffic, because you've got to have really large vehicles to be able to take that material away. Okay, here's a couple of questions for you on the limestone cycle then, and then we are going to move on after that to extracting metals. So have a go at these and then we'll go through them. Okay, let's go through these then. Complete the word equation. Calcium carbonate goes into calcium oxide plus carbon dioxide. These are all typical exam questions that you might get. What is the name given to this type of reaction? It is a thermal decomposition reaction. Suggest why the reaction in question 1 can be bad for the environment. This carbon dioxide and carbon dioxide can lead to global warming. Is calcium hydroxide an acid or an alkali? It is an alkali, that's why it is used to neutralize acidic soils. And finally, to make calcium hydroxide, water is added to calcium oxide. What type of reaction this is? It is a hydration reaction. So very well done if you got those correct. If not, you might want to watch the video back a little bit later. Right, so moving on then to a really big topic, which is extracting metals. Now, first of all, we need to know where metals come from. Now, some metals, like gold and platinum down here, are really unreactive. And you might just find those metals, just like in bottoms of rivers and things like that, and you might be able to extract them straight away. Other metals, because they're quite reactive, they will react with other stuff, normally something like oxygen, and they will make a rock like this. So things like iron oxide or aluminium oxide is a common way to find the rock. And the metal is then trapped in that rock, and we need to find ways of extracting it. Again, a really common definition that they might ask you, and in fact the examiners commented recently that people just don't get this, so I'm going to concentrate on this bit now, is the definition of an ore. Now, this definition is important because actually all rocks will contain metals. Okay, all rocks will contain at least some metals because they are metal compounds, but we can only call it an ore if this is true, that the rock contains enough metal for it to be economically viable to extract. Now, in layman's terms, that means it's got to have enough metal to make it worth it in money sense. So try and write this one down and remember it if you can, that an ore is a rock containing enough metal for it to be economically viable to extract. If you can't remember that, you need to think of the idea that it's got enough metal for us to be able to make money, so it's worth extracting. And how we extract that metal from that rock depends on its reactivity. And this is the other bit that you will get on your data sheet. You will get a reactivity series. And as soon as you get into the exam, you might want to write a couple of notes on here. It's called brain dumping if you want to write a couple of things on straight away. For example, you might want to quickly write that everything above carbon I'd need to use electrolysis for. And everything below carbon I can use some other forms of extraction. So a lot of this topic concentrates on this metal down here called copper. And there are several ways that we're going to talk about how copper can be extracted in the next couple of minutes. We're going to talk about phytomining. We're going to talk about bioleaching. And we are going to talk about the purification of copper through electrolysis. And this is where people get confused, because I've just told you that you use electrolysis for everything higher than carbon. So then people say, well, why are you using electrolysis for these things down here? That's because you can use electrolysis, okay? It will work just in the same way, but it's the case that if you're above carbon, you can only use electrolysis, okay? The other reactions that we'll talk about won't work. And the reason we're talking about copper, a really important thing to write down, is that copper is in really high demand because we use it for electrical wires and loads of saucepans and loads of electrical components and things like that. So in really high demand, but high-grade ores are running out. And that is a really common thing to be talking about in an exam paper, the idea that these high-grade ores are running out. And that just means ores where there's going to be a load of copper on it, so it's going to make loads of money. Okay, so it's going to be worth it to extract. High-grade ores would contain loads of copper, and low-grade ores wouldn't contain much copper at all. So let's go through a few of the techniques we can use then to extract the metals from these ores, these rocks. The first thing, this is a summary of everything we're going to talk about. We'll talk about reduction with carbon, talk about electrolysis, bioleaching, phytomining, and displacement with scrap iron. So loads of different reactions going on. First one I want to talk about is reduction with carbon. And you need to know that the word reduction means the removal of oxygen, whereas the opposite to that is oxidation, which will come up later in the topic. Oxidation is adding oxygen. Okay, and reduction is removal of oxygen. So it's basically using carbon to remove oxygen from its ore. Sorry, removing oxygen from that metal ore. So the ore that we're going to talk about in this question is iron oxide. Okay, so that would be the ore that we're using. And we're going to do a reduction reaction. So we're going to add carbon. The carbon is going to take the oxygen away, and we're going to end up with iron plus carbon dioxide. Again, alarm bells ringing for global warming. And this type of reaction, this type of process, you might see written in your exam as a smelting process. And it happens in something called a blast furnace. And sometimes they'll give you a really complicated diagram like this to try and explain what's going on. But essentially, you need to remember that this is happening. So the carbon here comes in the form of this coke. This coke is quite a pure carbon. And that is how the carbon is going into the machine. You would then have in the blast furnace your iron ore, so your iron oxide. And after a while, you'd end up with your molten iron coming out of the bottom of the blast furnace. And you'd have waste gases like your CO2 coming out to the top. Now, this reaction, importantly, only works for anything below carbon. So reduction with carbon only works for these metals here. It doesn't work for the metals above because carbon is more reactive than these metals. So it can come in, and it's a little bit like a displacement reaction. It can come in and take that oxygen away from the iron. If you had, however, something like aluminium oxide and you added carbon to it, nothing would happen. The carbon is not reactive enough to take that oxygen, and therefore nothing would happen. So that's the first way we can extract a metal from its ore. It's called reduction with carbon. The next way that we're going to talk about is a displacement reaction. And a displacement reaction is one where a more reactive metal comes in and displaces the less reactive metal. So a more reactive metal, and this is why you'll need your reactivity series, which you get on your data sheet as well. A more reactive metal displaces the less reactive metal. So, for example, in this case, iron is more reactive than copper. So iron will react and it will take away the sulfate and leave you with the copper. So you'd end up with iron sulfate plus copper. Similarly, you might have another example like lead sulfate plus zinc, for example, and try to think about what you would end up with if those two things reacted, lead sulfate and zinc. Well done if you thought that would be zinc sulfate plus lead. Okay, so if you see these kind of reactions, you need to remember it as a displacement reaction. There's not reduction this time because we're not removing oxygen. We're talking about removing a sulfate, which is completely different. Okay, so this is the displacement with iron. And the advantage of this is that we can use scrap iron. So we can use really cheap iron that we don't want anymore, chuck it in, and we can get our copper. And that is the thing that is in demand because high-grade copper ores are running out and we're in a massive demand for this copper. Okay, moving on then to phytomining. Now, I've repeated it several times because it's so important, the idea that high-grade copper ores are running out. So we are wanting to develop new technologies like phytomining, which allow us to use low-grade ores. Because we might have a few areas where we've got ores of copper, but they don't contain much copper in. But if we can develop new technologies to get this copper out of these low-grade ores, then this is going to be a bonus. So the type of thing that you need to remember for phytomining is the idea that you would have your low-grade copper ore containing your copper, and onto that you would then grow some plants. And your plants would then absorb the copper through its roots. Okay, so the roots going down, the plants will absorb minerals, including copper. and then you would have the copper collecting in that plant. Now your next step then would be to harvest that copper by harvest the plants by chopping them down, and then you'd want to burn those plants. And what you'd end up with is, after you've harvested them and after you've burnt them, you would end up with an ash. So we'd have our ground there, and on that we'd have our ash. Now there's no easy way to separate copper from that ash, and this is where most people are understanding of phytomining stops. We need to think about how we could then separate that copper from that ash. It's not magnetic, we can't use a magnet to take it out, we can't filter it out. So instead what happens is they add a little bit of sulfuric acid, which is H2SO4. And if they then add sulfuric acid to that, you can make a solution called copper sulfate. Okay, so the copper in that reacts with the carbon dioxide and you make copper sulfate. And you've probably used that in class before. It's that funny blue liquid that you're not allowed to pour down the sinks. Okay, that copper sulfate can then be put into an electrolysis equipment, and you can then extract the copper. So quite a long-winded process. I've seen this as a 6 marker before, and people kind of got stuck on that stage. You need to remember that now the copper's in the ash, we need to add some sulfuric acid to make that copper sulfate, and then we can use the process of electrolysis. Now I'm going to just discuss electrolysis in just a sec, so I'll just leave it there for now. Okay, next we're going to talk about bioleaching. So whereas before we said that phytomining was plants, P and the P stand together, phytomining for plants, bioleaching is using bacteria. Again, a new technology because high-grade copper ores are running out. Bioleaching uses bacteria. And what you would do is you would have your copper ore and you would grow your bacteria on that ore. And the bacteria are really good at separating copper compounds. So the bacteria separate copper compounds. It's really good for them because they get some energy by doing that. So they separate the copper compounds like copper sulfide, for example. And then they produce a leachate solution. Okay, so we need to remember that leachate solution. Bacteria produce that leachate solution containing copper. So you don't need to go into detail about this process. So don't worry if you can't remember much about it, because all you need to know is that bioleaching involves bacteria. The bacteria separate copper compounds and they produce this leachate that contains the copper. You can then go on to filter that copper out because it will be in solution, or you could do like we did before, add some sulfuric acid and do electrolysis. So moving on then to electrolysis, we're going to talk about the simple setup of electrolysis that we'll see for C1. Importantly, let's refer back to this reactivity series. We said that everything above carbon, you can't reduce it with carbon. You can't really use displacement reactions because these things start getting expensive up here. And you don't see it used for phytomining and bioleaching. So instead we have to use electrolysis. But there are a few downsides to electrolysis. I try and remember them because they all start with the same letter. It uses lots of energy, E, and it's expensive. So it's an expensive process. You want to avoid it if you can. That's why down here, rather than using electrolysis, you might want to use displacement with scrap iron or reduction with carbon or something like that. So what happens in electrolysis then is the splitting up of a compound using electricity. So in that electricity, you would have, in that process, you would have a circuit connected and you'd have two electrodes connected to your circuit. One would be positive and one would be negative. Then let's use the example of copper sulfate, for example, because you would have seen that blue solution that you would have used in the lab before, I imagine. In that, you've got your metal copper ions that are free to move. And if you remember from before, you should be able to remember whether copper ions will be positive or negative. Well done if you remembered that they would be positive. Cu2 plus for copper ions, and then you'd have also your sulfate ions in solution as well. And for electrolysis, the key process that we need to remember is that opposites attract. So the positive ions will move to the negative electrode, and the negative ions will move to the positive electrode. Now, you may well know or may well have been taught of different words for these. You may well have been taught about this being the anode and the cathode, but I would strongly recommend that you don't try and use those terms in the exam, because they're often people get confused about those ones. Just play safe and use positive and negative electrode. So the positive ions then move to the negative electrode, the negative ions move to the positive electrode. So you would have your copper ions moving towards your negative electrode. Okay, and that is where the copper will collect. It will collect on that electrode there, and you can then pull it out. Now, I also remember positive copper. If you try and remember a smiley policeman, that might help you out. Okay, so smiley policeman with his hat on, that will remember you that copper ions are positive. Also, if you forget that, don't forget that you get this on your data sheet. So no guessing. Okay, if you really can't remember, there's no need to guess. They are here, and it tells you copper is Cu2+. Tells you it's positive. Tells you a load of negative ions here as well, in case you need them. So there really is no need to be guessing. Okay, as well as the basic separation of metal compounds using the purification of copper, using electrolysis, we also need to know about the purification of copper. And that is when you have special electrodes. So you will still have your negative and your positive electrode, but you want to have a really impure piece of copper with loads of impurities in it. And you want to transfer those copper atoms that you have here across to a block of pure copper. So if you've got an old straggly bit of copper with loads of impurities in it, so loads of other elements, maybe bits of carbon or bits of sulfur or main bits of the compound or the ore that it comes from, you want those copper ions to be transferred over to a pure piece of metal. And you can do this by electrolysis. So it's important that you have the electrodes the right way around. And if you remember that copper is positive, it moves the negative electrode. You should then remember that the pure piece needs to go at the negative electrode, and the impure piece needs to go at the positive electrode. So the movement of ions that you will see will be positive copper ions to the negative electrode. Now, the solution that you'll see it in still needs to contain copper. So this might be something like your copper sulfate solution. And I should have remembered before to say that this is called the electrolyte. So the solution that is in the process of electrolysis is called the electrolyte. And this has to contain copper as well. Otherwise, you might get different metal ions moving over there. So this might be something like copper sulfate, that blue solution that I mentioned earlier. So that's what happens in purification of copper. It's really common in the exam for them to ask you which electrodes you should put the pure or impure copper on, or they may use a wrong electrolyte. They might use like silver nitrate or something and ask why that is a problem. So hopefully some of that's sunk in for you. Let's test you with a few questions here. And post any more questions that you've also got on YouTube or on the Frog page as well. Have a go at these questions and then I'll come back and see how you get on. Okay, just 30 more seconds and then we'll go through and see how you got on. For those of you who have just joined, feel free to watch the end of this tutorial and then you can always watch it again either on my YouTube page or if you're at Nosewood on the Frog archive. So question 1 then says suggest a method, oops sorry, keep doing that, suggest a method to extract magnesium from its ore. So if we look here, magnesium is more reactive than carbon, so we can't use any of those reduction with carbon or displacement methods, so instead we must use electrolysis. Question 2, can scrap iron be used in a displacement reaction to extract zinc from its ore? Now zinc is more reactive than iron. Therefore, in this question, can scrap iron be used to displace ink? No, it can't. Because iron has to be more reactive than things that it's displacing. If you had zinc oxide, for example, and you added iron to that, nothing would happen. Whereas if you had tin oxide, that would be okay because tin is below iron and you would end up with iron oxide and tin left over. Question 3, what is an ore? Hopefully you remembered that from right back at the beginning when we were talking about extraction of metals. An ore is a rock that contains enough metal okay, and you could say to make money, that would be fine, or the phrase that they like is for it to be economically viable. So for it to be economically viable. Fourth question, in the purification of copper, on which electrodes should the piece of impure copper be? Well, don't forget the copper ions are positive, they'll move to the negative electrode, so you would want the impure bit to be on the positive electrode. And why are new technologies like phytomining and bioleaching be developed? Well, that's the idea that copper is in high demand and that also, as well as it being in high demand, that high-grade ores are running out. So very well done if you got those correct. I've just remembered that on the previous slide, I just want to mention one more thing just quickly. When we're talking about the purification of copper, I just wanted to mention that when you've got your positive and negative electrode, with your impure copper on it and your pure copper, just last thing to mention, you will get sludge at the bottom. That's where the impurities fall. Okay, so apologies for not mentioning that earlier. When you get the copper ions moving across the negative electrode, you'll end up with impurities forming as sludge on the bottom of the tank. So that brings us to the end of this revision tutorial. So very well done if you feel like you've got something out of that and you could answer most of those questions. If not, then feel free to watch it back over. I'll edit it and clip it for you to watch. And I will do the same thing to include another tutorial about fractional distillation and alkenes, alkanes, emulsions, and everything else that comes up. So thanks very much for watching. I'll be happy to answer any further questions that I get on Frog or YouTube. Just one final question that's just come in just before we go that says, why does the electrolyte have to be copper sulfate, for example, to extract copper? Well, that is because if you had something else, let me get my pen up here, if you had something else in that rather than copper sulfate, so in this electrolyte, I said it's got to be copper sulfate, because the copper ions are then allowed to move in this electrolyte because it contains copper. So at the negative electrode, if we do these basic electrodes, at the negative electrode you will get copper, sorry, at the negative electrode you will get the copper collecting here. And the reason, to answer your question, that it's got to be copper sulfate is because if you had silver nitrate in here, for example, then you would have silver ions that could then go and be attracted to your electrode. And you wouldn't want that because you just want the copper going there. So if you use silver nitrate or something else with another metal in, then you would have other metals attracting to that electrode, when all you want is the copper going to that electrode, hence that you want copper here. If you're doing the purification, you have to have a electrolyte also containing the copper sulfate as well. So I hope that's answered your question. Thanks very much for watching, and that brings to a close this revision tutorial.